Relative humidity can be calculated in two ways. It can either be calculated by taking the mixing ratio and divided by the saturation mixing ratio, or taking the vapor pressure and dividing by the saturation vapor pressure. The actual value you get will measure how close to saturation you are. A calculation of 100% relative humidity means that you are at saturation. Now, saturation vapor pressure is dependent on temperature. In the graphic below, in blue, you see depicted what could be seen as the actual amount of water vapor in an air parcel. This corresponds to the value of the actual mixing ratio. In yellow, you have depicted the value of the saturation mixing ratio. You'll note that at different temperatures, you have a different saturation rate mixing ratio, with the amount of saturation mixing ratio increasing with temperature, so that the same amount of water vapor or actual mixing ratio at different temperatures will yield you a different relative humidity. Dew point is perhaps the most common measure of atmospheric humidity. Again, it's defined as the temperature to which an air parcel must be cooled in order for dew to form and for water vapor to begin to condense into liquid form. Below freezing, the dew point actually becomes something called the frost point, because water will no longer condense in a liquid form at that point on a solid surface. It will instead deposit as ice. So the chart below depicts a dew point of 10 degrees Celsius in each of these three cases. Note that although the temperature changes, the amount of water vapor doesn't change. Hence, the dew point remains at 10 degrees Celsius in all these instances. In other words, if you cooled any of these parcels of air to 10 degrees Celsius, water would start to condense.